All right, friends, welcome to Chapter 2. We begin with 2.1, conditional statements. A lot of words in this section, my friends, a lot of vocabulary. And we are training ourselves to think like geometers. And we start to write proofs, which is usually the most challenging thing that geometry students have to encounter. The proofs will be in these types of forms, so we need to start thinking logically. And the first step to that is to analyze conditional statements. So, what are we doing here? Our essential question is, when is a conditional statement true or false? A very important concept. A conditional statement symbolized by P arrow Q. So this very important notation we'll be analyzing this section. And really when you read it, it's if P then Q or P implies Q. Any of those things mean the same thing as P arrow Q. Example, if a polygon is a triangle, then the sum of the angle measures is 180 degrees. The hypothesis is the if or the P part, and the Q, the conclusion, is the then part. So our first exploration, I want you guys to try this on your own. Pause the video and follow the directions here and see what you got. All right, welcome back. First exploration. A hypothesis can either be true or false. The same is true for the conclusion. So the first part could be true, the second part could be true. For the conditional statement to be true, the hypothesis and conclusion do not necessarily both have to be true. Determine whether each conditional statement is true or false. All right, so a nice setup here in the directions. First one, if yesterday was Wednesday, then today is Thursday. All right, that's true. If an angle is acute, then it has a measure of 30. Not necessarily. That's false. If a month has 30 days, then it's June. Again, not necessarily. There are other months that have 30 days, just like there are other angles other than 30 that could be acute. If an even number is not divisible by 2, all right, now this one's tricky. Then 9 is the perfect cube. So check this out. The hypothesis is false if an even number is not divisible by 2. So this is a difficult concept we'll talk about in class. So then let's look at the conclusion. Then 9 is a perfect cube. Well, that's false also. So when you have a false hypothesis and a false conclusion, this actually produces a true conditional. So true, false, false, and then true on this one. Even though both of the things inside of it are false, it's kind of like this, if the hypothesis is false, it throws the whole thing off and anything can be true. So true is how you'd actually have to answer that one as a conditional statement. All right, pause the video for exploration 2 and see what you got. All right, welcome back. Work with a partner, determine whether each conditional statement is true or false. All right, so first one, if ADC is a right triangle, then the Pythagorean theorem is valid. So I got a true here, so the whole thing's true. If A and B are complementary, all right, so say and I got a true statement there, then the sum of their measures is, ooh, that's bad. So that produces a false statement. If ABCD is a quadrilateral, then the sum of its angle measures is 180. Nope, that's false, which makes the whole thing false again. If points A, B, and C are collinear, then they lie on the same line. That's true. So the whole thing is true. If A, B, and BD intersect at a point, then they form two pairs of vertical angles. So again, a true yields a true. So the only time you have a false when you're analyzing a conditional is if, in the cases of B and C, where true hypotheses lead to false conclusions. All right, then you have to throw the whole thing out and call them false. So when you're answering, communicate your answer here at the bottom. When is a conditional statement false? Well, it's only false when a true hypothesis produces a false conclusion. All right, everything else in the world of logic is true. Even the one we had in exploration 1, where we had a false and a false, that gives you a true. Even a false and a true gives you a true. The only thing that leads you to a false path is a true hypothesis and a false conclusion. All right? And of course, if you have true and true, that's going to be true. So the only time our if-then statement is false is if you have a true hypothesis and a false conclusion, like evidenced here and here. All right, now into the main stuff of the section. Conditional statements, a logical statement that has two parts, the hypothesis and conclusion, if-then form, and again, here's how we'll see it. P implies Q, P arrow Q, if P then Q, all these things mean the same thing to us. It's a scenario, it's a condition. You can go, if I go to the mall, then I had enough money. There are conditions that allow you to do things. First example is actually rewriting a statement in if-then form. So a statement could be like part A here, all birds have feathers. Well, how could we turn that into a conditional? If an animal is a bird, then it has feathers. So you add the if and the then, and it has to be logical. You can't say if all birds, then feathers. What is a bird? It's an animal, so refer to it in its proper form grammatically to make sense. Part B, you are in Texas if you are in Houston. So we can make that logical sense of that. If you're in Houston, then you're in Texas. Right? Okay. Next, let's see, negation. Ooh, an important concept here. A negation is the opposite of the original statement. So let's see, to write a negation, ooh, important symbol here. The little similarity symbol, or it has a word name in Spanish I'm not sure of, but it's an accent aigu, maybe, something like that. But in the world of logic, it means not. So when we see not P is going to represent the little squiggly P. Or you could have squiggly Q, not Q. And here's what it would mean in example 2. Write the negation. So of course, the ball is red. The negation is the ball is not red. And if you have not in the beginning like B, then you take it out. The shoes are not red. The shoes are red would be the negation. All right, more words, my friends, more words. Consider the conditional statement below, if P then Q. We have 3 things we can do to a conditional: a converse, an inverse, and a contrapositive. And the symbols kind of dictate what's happening. To write the converse, you just flip the hypothesis and conclusion. To write an inverse, you keep them in the same order, but you include nots. And the contrapositive is when you do both. You flip it and you put nots in. A conditional statement and its contrapositive are either both true or both false. So the conditional and its contrapositive are always logically equivalent. So they'll either be both true or both false. And the same thing holds true for the converse and the inverse. All right? These two will be the same truth value as well. All right, so let's analyze what this means. Here we go. Let P be you are a guitar player and Q be you are a musician. So we want to put that as an if-then statement, the conditional statement, and then do these 3 things to it. So first, take guitar player, musician. So if you are a guitar player, then you are a musician. That is a true statement. All right? So the converse is then, we're going to flip it. And we're going to say, if you are a musician, then you are a guitar player. And of course, that is false. You could be a musician by playing other things. The inverse. Now you keep the order the same. Guitar player is first still. Musician is second. So if we're flowing with this, this is your P and this is your Q. So in the converse, we put it as Q to P. And then in the inverse, we keep the order the same, but we put nots in. So we say not P, not Q. So if you're not a guitar player, you're not a musician. And that's false. You could play something else. And then, of course, the contrapositive says you flip it and you put knots in. So now it's looking like not Q, not P. All right? So if you're not a musician, you're not a guitar player, and that is true. If you're not a musician, then you're not, couldn't possibly play the guitar because you don't play anything. And again, logically equivalent. These two and these two will either be both true or both false. All right, good definitions. You can write a definition as a conditional statement in if-then form, or as its converse. Both the conditional statement and its converse are true for definition. So to be a good definition, then both conditional and converse are true. For example, consider this one. If two lines intersect to form a right angle, then they are perpendicular lines. There's the definition of perpendicular lines, and it's written in if-then form. You can also write the definition using its converse. Flip it. If two lines are perpendicular, then they intersect to form a right angle. And since that's also true, you can rewrite it as what we're going to talk about in a second, a biconditional. So you can write line L is perpendicular to line M as L upside down T M. All right. Example 4, decide whether each statement about the diagram is true. Explain it with a definition that you have learned. So in part A, AC is perpendicular to BD. Yes, that is true. AEB and CEB are a linear pair. AEB, CEB are a linear pair. That's also true. EA and EB, they are not opposite rays. So you want to explain it. Here you go. The first statement is true by definitions. And of course, C, the statement is false. Also reverting back to the definition of opposite rays. All right, pause the video here, pick it back up, see what you come up with. All right, friends, here we go. JMF, so this angle, JMF, and angle FMG are supplementary. That would be true. Point M is the midpoint? Nope. We don't know, do we? M is the midpoint? No, we don't know that that segment is congruent to that. They'd have to tell us that. JMF and HMG are vertical angles. Yep, that's true by definition. So the definition will be your explanation. And are they perpendicular? That's false. We would need more information. We would need the right angle symbol there. All right, and finally, a biconditional. So biconditional, two conditionals. And the key thing we want to remember is the phrase if and only if, and the double arrow symbol. Biconditionals, when a statement and its converse are both true, then you can combine them to write an if and only if statement. Here we go, last example. Rewrite the definition of perpendicular lines as a single biconditional. If two lines intersect to form a right angle, then they are perpendicular lines. So there's your P and your Q. All right. So the definition, written as PQ, if two lines intersect to form a right angle, then they are perpendicular. Flip it. So that was P to Q, flip it, Q to P. If two lines are perpendicular, then they intersect to form right angles. It's true. It's true. So when that happens, when you have a conditional and its converse both being true, you can combine them to form a true biconditional. Two lines intersect to form a right angle if and only if. So there's your key phrase there. They are perpendicular lines. So it takes the if and the then out, and it includes if and only if. A lot of words in this section, my friends. All right. Peace.